Friday, Tuesday that I've gotten going of late. So anyway, on the board here, if you just came in, you should grab your cell phone, take a picture of this whiteboard. It is a very, very nice overview of really sections 4.4, 4.5, and even some of 4.6. Okay, I'm going to now talk through it though with you. So I want everybody to feel really solid about this, and then we're going to do 4 warm-up problems, and then you guys are going to do some group work problems as well. So we're going to get a lot of practice on the stuff that's on this board. Okay, so first thing is somebody gives us a set of vectors, right? A handful of vectors. I'm calling that S. I want you to notice that I'm going to start using K for the number of vectors. So my set has vectors v1, v2, v3, and so on up to vk. Those vectors, they could be polynomials, they could be matrices, they could be functions, they could be physics vectors. Any of these standard vector spaces that we've been working with, that's what I'm talking about. And on Tuesday, we introduced what is really the fundamental definition about vector spaces, which is the idea of a basis for that vector space. Okay, really, really important idea. A set of vectors is a basis if it is a spanning set for the vector space. In other words, S spans V. And secondly, S needs to be Li. Li means linearly independent. In other words, those vectors need to be cheap. They need to be not redundant on each other. So we're looking for an efficient or a cheap set of vectors that spans our vector space. Okay, and if we have that, we're calling it a basis for that vector space. Really, really important idea. Okay. When we're thinking about whether our set spans V or whether our set is Li, the good news is we've learned some tests for both of those, right? We have a spanning test and we have an Li test. And they're very similar to each other. In both cases, we lay the vectors that we are given into the columns of a matrix. And what we will do is we will augment that matrix depending on which test we're doing. If we're doing the spanning test, you might remember that I like to use just those number symbols into the far right augmented column. And what we're looking for there is after we do the EROs, we are asking ourselves, is it a consistent system? Does it have a solution? If it does, that's a good thing. And that will mean, yes, your vectors do span V. If the system is inconsistent, well, that's a bad thing. That would mean no, the vectors don't span V. So it's yes or no, just according, really it just comes down to whether there's a pivot that goes into that far right column. When it comes down to it, that's really what you're talking about. So that's the spanning test. And like I said, the Li test is almost the same thing. You lay your vectors into the columns of this matrix again. For the Li test, instead of number symbols, we will be augmenting the matrix with a column of zeros instead. This time, the issue is not whether it's consistent or not. The issue here is whether there are any free variables or not. So actually, you don't want free variables. If you have no free variables, that's a good thing. That means, yes, your vectors are Li. Okay. But if you get free variable, remember, what is a free variable? A free variable is associated with an unpivoted column in your row echelon form. If that happens, what it's really telling you is that you could make your vectors cancel out in a linear combination in an interesting way. In other words, that the vectors are LD if that happens. If you have free variables, that's a bad thing. It means the vectors were too expensive. You have dependencies among them that you didn't need to pay all this extra price for, right? You don't really want to have that. So anyway, this is really good for everyone to know because these two tests are going to be needed anywhere. In a minute, I'm going to talk about this chart. You see some question marks in the chart. When I have those questions, these tests are going to help me answer those questions. Okay, so I'll get back to that in just a second, but is everybody Feeling all right about this? You've probably already been doing this a fair bit in the homework, even for the last assignment. Writing out your vectors into the columns of a matrix and augmenting it with either number symbols or zeros, and we can do them simultaneously. You saw me do the zero slash number symbol thing last time, right? You can do them both in one go if you want to, but these tests are certainly going to be things that everybody needs to know how to do. Okay. Now, I mentioned on Tuesday that a vector space can have lots of different bases that are all correct. We could have 35 people in this room. We have 35 different bases for R3 or for P5 of R or whatever vector space it is. So there can be lots of spanning sets that are Li, lots of bases, but any basis for V will always have the same number of vectors in it. That will be the common thread among the different correct bases for your vector space, right? And that number of vectors is the dimension of the vector space, okay? So one thing I want everybody to be memorizing are these very familiar dimensions of these very common vector spaces. So the dimension of Rn, we talked about this on Tuesday, it's n. The dimension of Pn of R, that's n plus 1. Guys, you really want to know these cold. You want to be like in the shower, be able to come up with these numbers. You don't want to have to like fumble around and think of the answer. Just whatever you're doing, whenever you're doing it, this should just be like second nature. Second nature. So if you need to, make some flashcards. Put the vector space on one side, and then on the back side, write down what its dimension is, and see if you can test yourself and get these numbers right every single time. Okay. One reason why it's so important to know these dimensions is that if I want to use this table, the dimension of V is part of what you need to know in order to be able to apply the table correctly. Okay? What is this table about right here? Well, this is my favorite question for midterm too. I give you a set of vectors, and I ask you, are those vectors a spanning set for V? Are they Li? Or are they actually both? Or are they neither? It's a really common question you'll see that I will likely ask. And how to answer this question, it's a 4-part multiple choice question. But what you might notice is that depending on how many vectors I gave you, so if K is the number of vectors given, if we compare that to the dimension of V, which we can only do if we know the dimension of V. That's why I want you to know these numbers, right? If I know the dimension of V and then I give you a certain number of vectors, then I can compare and say, well, is K less than the dimension, more than the dimension, or equal to the dimension? And then based on that, so let's just take the first row here. If I give you less vectors, if K is less than the dimension of the vector space, then can S be a spanning set for V? No way, right? It's a no for sure. And if it's not a spanning set, then it's definitely not both, okay? It might be Li. I put this question mark here because if I give you less vectors than the dimension of V, then those vectors could be Li. If I want to really answer this question, I have to use my Li test at this point. You see, that's why the Li test, it comes into play here. So it can help me decide on this, right? And it'll either be a yes or a no. If it's a yes, then your vectors are Li. Otherwise, you end up with neither in that case. Okay. The opposite scenario, if I give you too many vectors, well, if I give you too many vectors, then there's no chance that they could be Li. I've paid way too much money for those vectors. They're not Li, so they're also not both. The question here would be, maybe they're a spanning set. And I would have to use the span test to decide whether they were really a spanning set for V or not. Okay. And then the last scenario is, well, what if I give you exactly the right number of vectors? So I know what the dimension of V is, and the number of vectors that is in front of me is exactly the same as that. Well, then it turns out that those vectors will either be both or neither. You can't have one without the other. It will not be only a spanning set, and it will not be only Li. It will either be both or neither in that case. And in that case, by the way, in this last row, when the K and the dimension of V match each other, then when you lay those vectors into this matrix, it's going to form a square size matrix, and you can actually use the determinant to decide whether it's both or neither. Okay, I didn't put that all in the recap here, but we talked about that last time. Okay, does that make some sense? What I'm trying to say, guys, is that if you know the dimensions of your vector spaces, and then somebody gives you a set of vectors, then as long as you know how to count up to like 5 or less, then you're probably going to be able to figure out what K is, figure out what the dimension is, and rule out 2 of the 4 wrong answers immediately without even having to break a sweat, right? Super easy. It'll just be from this table, you'll know what the conclusion is. But in any one of the rows of this matrix, you do have to do some work because there are question marks here. The other thing I wanted to point out, you notice how many times you see the word yes in this table? You don't see it anywhere. That's because we cannot say a fast yes on these Li and spanning questions ever. Okay, I could give you 500 vectors in R3. I still don't know for sure that they span it. Right? I still don't know that for sure. I'd have to test that to make sure. So it is sometimes you're going to have to do some work, but it would be nice to know where the definite no's are. You can say it's definitely not this or definitely not that, just based on this table you see. Okay. So this is a really nice overview. I didn't used to have this, but I've kind of decided this is a good table for people to take a look at. Let's try a few warm-up problems that are kind of going to use some of the stuff from the table so we can kind of see how it comes into practice. And we've done some of these kind of things already, but I don't mind spending a little more time on this to get us going today. So the first warm-up that I want to do is I want to ask you, is the set of 3 plus x, comma, 4 minus 2x, comma, 6 plus 3x, is that set a basis for P1 of R? So we can ask this question, do those 3 polynomials form a basis for P1 of R? Okay. So if I see a question like that, the first thing I'm going to do is remind myself about what the dimension of my vector space is. What is the dimension of P1 of R, guys? 2. It's 2, right? According to the formula over here, the dimension of Pn of R is just n plus 1. And what is my K value? How many vectors did I give you here? 3. Okay, so let's compare the K with the dimension. I go into my table, K is actually more than the dimension of V, right? So if K is more than the dimension of V, then we have a no on the Li question. So if it's not Li, then it's not a basis, right? Because to be a basis, you got to be both. You got to be this is the basis column right here, right? And we're not there. We're getting, we're basically along here, and we've got a no on the basis spot. So this is already a no. I can already say that it's a no. And the real issue is that S cannot be Li. It cannot be Li. It's a no right here on the Li part. Now, these vectors might be a spanning set for P1 of R. That's where we would have the question mark right here, right? They might be a spanning set. Let's say we wanted to have a follow-up to ask that question. So as a follow-up, the follow-up would be, is this a spanning set? Remember, guys, let's not forget what a spanning set is. A spanning set is a set of vectors such that if you take all possible linear combinations of those vectors, that you would create the entire vector space. So that you would be able to write any polynomial of P1 of R in terms of these guys. Okay, so spanning sets are, even though we've already, it's a lost cause on being a basis, but it'd be nice to know if it's a spanning set, because even though it's maybe too expensive, it was too expensive, but at least it might have this good quality that the vectors do actually span the entire vector space. So I'm gonna do my spanning test here that's on the board. So I lay my vectors into the columns of the matrix. The first vector is 3 plus x. I'll write that as a 3 and a 1. The next vector is 4 minus 2x. I'll write that as a 4 and a negative 2. And the next vector is 6 plus 3x. And I'm going to augment this with my number symbol, arbitrary values, right? So this is the setup of the matrix that we would need in order to answer this follow-up question. Okay. Now, obviously, I need to do an ERO or two here. I'll probably want to permute my two rows. So I'll switch the order of those two rows. I'm going to circle my pivot here. And I'll put the first row second and the second row first, like that. And let's see, I guess I should probably make the value that's below that pivot into a 0. So I'll just do one more step here, guys. If I take -3 times the first row and I add it to the bottom row, I should get 0 and 10 and -3. And remember that these number symbols just keep coming along for the ride. I don't have to do any algebra with those. I just have to keep recopying those down. And let's circle the 10 is technically not a pivot. So I mentioned on Tuesday, guys, that we're getting a little bit more comfortable, hopefully, with EROs and pivots and stuff like that. We really don't need to make this into a 1. All I really care about are the positions of the pivots. You guys with me? Mm-hmm. Based on this, would you tell me that it's consistent or is it inconsistent? It is consistent, isn't it? Because there's no pivot in the far right column. So this is consistent. There's no pivot drifting over onto my number symbol. And what's my test say? If it's consistent, then the answer is yes, you do have a spanning set. So we at least have salvaged that part. Okay? Everybody with me? Actually, there's another reason why you might set up this matrix, aside from wanting to know if it's a spanning set. As soon as I know that the set is not Li, then I actually know that it's LD. And one of the questions you're going to see if you look at the homework for tomorrow, a lot of you have already looked at it, I know that, but if you look at the homework for tomorrow, if the vectors are LD, they will sometimes ask you to write down a linear dependency. Now, I went through this on Tuesday a bit, but just to reiterate how that works, you've got constants associated with these columns. And so with this matrix, so the only thing that would be different if I'm looking for linear dependencies is I would be augmenting the matrix with zeros instead of number symbols. So if I come back to, I'm kind of backtracking for a minute here, guys. I'm trying to go back to the LD part of this. These vectors are LD. How would you actually get the linear dependency? Well, I just wanted to remind you about this. This is also reviewing from our last class. What you basically need to do here is set up a free variable for C3, which would be T. The third column does not have a pivot. It's because of that free variable, right? It's because of that free variable that the answer is no, it's not Li, right? Mm-hmm. And now I have to back substitute and solve for C2. And just to make a long story short, C2 is going to be 3/10 of T. I will save you a little bit of the headache of writing that all out. And then C1 would be equal to, well, C1 would be equal to 2C2 minus 3C3. So 6/10 of T minus 3T, like -24/10 of T, I believe. Hope I did that right. I think I did. So you solve for all of your unknowns in terms of the free variable. We've been doing this for weeks now, right? And as I mentioned on Tuesday, you now have to just choose a value for t. I almost always will just choose 1. You can choose any number that you want, guys, except for 0. Just don't choose 0 for your t value. But as soon as you've done that, then you can write down, okay, so C1 is negative 24/10, C2 is 3/10, and C3 is 1. And once you've got that, you can make your linear dependency. So how does that work? Well, C1, which is negative 24/10, times my first vector, which was 3 plus x. So now I go back to my original vectors. And then plus 3/10 times my second vector, which is 4 minus 2x. And then plus my last vector is 1 times 6 plus 3x. And if you crank that out, I can tell you already that you have to get 0 out of that. This is the linear dependency right here, guys. This is the linear dependency that we are looking for. So just with this one example, I'm only on warm-up problem number 1, but we've certainly reviewed a lot of stuff already, right? Basically, here's a set of vectors. They were not a basis. We had that figured out a long time ago. But then the follow-up question is, well, are they at least a spanning set? Turned out that was a yes. But because they're not Li, we can actually write down a linear dependency here. So the whole thing kind of shakes out like that. Okay, let's try another one. Are there any questions on that though? So far, so good? Okay. Is that a yes? Okay, fantastic. Let's do number 2. So here it is the following. I'm going to make another set. Let's do 117 minus 89x, comma, 51 plus 261 x squared. And the question is this a basis for P2 of R? So I'm on a little bit of a polynomial kick here to start off today, two examples with polynomials. Okay. So same question as before, right? We're doing the same thing we did before. And when you open up the homework for tomorrow, you see all those problems in section 4.6. Some of them are this kind of problem. Is the set that they give you a basis for your vector space? And you see how fast you can get the answer sometimes. Let's try it here. Let's figure out the dimensions and all that good stuff. What's the dimension of P2 of R, guys?
3.
Okay, n plus 1 would be 3 in this case. How many vectors did I give you?
2.
2. K is just 2, right? So in this case, the K is less than the dimension of the vector space. So that's already going to be a no. That's already going to be a no. And specifically, if K is less than the dimension of V, the problem is they can't span it. They will not be a spanning set. They might be Li this time, but they're not a spanning set. So this is not a spanning set. So that's kind of dead in the water right away. We can't have a basis if we don't have a spanning set. I would like to ask, is this set Li? So again, we'll approach this follow-up question. So this is another follow. This is the same follow-up I was doing earlier on the last example. I just want to follow up again and ask, would it be Li? Because that's this little square right here, which we don't know directly whether it's Li or not. Now I have an Li test, right? Where I lay my vectors into the columns and then I do EROs on it. Now I chose to make these numbers pretty horrendous on purpose because I want to encourage you to not do EROs. Is there a way to decide whether these vectors are Li just by looking at them? Bypassing the Li test, is there something faster when we have only 2 vectors that I might have mentioned on Tuesday?
If they're scalar products?
If they're scalar multiples
Multiples.
of each other, right? Can I take, so I mentioned that on Tuesday, when you have only two vectors, when k equals 2, you can decide whether they are Li just by glancing at them, just by looking at them. Are they scalar multiples of each other or not? Now, in this case, can I take 117 minus 89x and multiply that by a number and have it turn into 51 plus 261x squared? It's not even the correct powers of x, right? I mean, here you have an x squared, here you don't even have an x squared. I would say no. These are not scalar multiples, and that means that this is a yes. And the reason here is we have two vectors. It's important that it's two. I made a big deal about this last time, that if it was 3 or more vectors, you have to use the Li test. You can't just glance at them. But we have two vectors that are not scalar multiples. So that's your justification. It is Li, but it's not a spanning set. So it's not a basis in this case either. So far, so good? Questions on anything up here yet? Yeah, don't be shy, guys. I'm always happy to answer questions, and I get excited and people are like, oh, I don't want to interrupt him, he's on a roll. But I'm like, yes, you do need to interrupt me sometimes. So if that's you, feel free to jump in.
Dr. Adams?
Yes, go ahead, Arlene.
So to check linear dependency, we can just plug in any number for x and if it equals. 0.
Did you see me plug in a number for x anywhere?
I mean, for the final answer, just to check to see if it works.
Oh, if
like,
it- oh, to
for,
see if
like
it-
sanity check.
Oh, a sanity check. You
Yeah.
could do that. It would be actually better to just simplify the left side with the x now, just to make clear. If you actually work this out, if you like multiply this all out, you should see everything on the left side cancel.
Oh, okay.
Yeah, just algebraically it should cancel. That's a good point. Absolutely. Okay, let me actually give you a couple more warm-up problems that are slightly different now. Okay? So here's number 3, but this one's a little different. This one is going to say find a basis. Find a basis for V, which is going to be the span of, I've got some matrices this time. 2 by 2 matrices. The first one is 1, 3, -1, and 2. The second one is going to be 0, 0, and 0, and 0. The third one is going to be -1 and 4 and 1 and 1. And the last one is going to be 5 and -6 and -5 and 1. And for those of you who are playing along at home with the homework, I will just tell you this is actually one of your homework problems for tomorrow. It's number 32 out of section 4.6. So I'm going to do one of your homework problems as my warm-up example here. So let's see how this might work. This says find a basis for V. Now I have to be really clear about something. V is not M2 of R. It's not. V is this thing right here. It's the span of something. So let me just remind you with my every day I have to come in here and say it at least once. Anytime you take the span of anything, you always get a subspace, or in other words, a vector space. So this is a vector space, but it's not M2 of R. What it is it's just all possible linear combinations of these 4 matrices. Actually, in a minute, we're going to see that its dimension is not 4. If it was M2 of R, its dimension would have been 4. But in a minute, I'm going to find a basis, and it's not going to have 4 vectors in it. It's going to actually be a different number. So this is not, you can imagine the big, huge universe that this problem is kind of framed in would be M2 of R. But this vector space is something different. It is just all possible linear combinations of these matrices that I've given you. Everybody with me on that? So I have another idea for finding a basis for this. Would it just be these four matrices? Obvious thing, they're just sitting there. Well, what I can tell you definitively, and this will be true all the time, anytime your vector space is expressed as a span, the vectors that are in here, they may or may not be a basis for V, but they are definitely a spanning set for V. I'm gonna put a check mark on that right now. They are a spanning set for V. Let's try to explain that. Guys, the reason that these vectors are a spanning set for V is because V, by its very definition, is the span of those vectors. You have actually used these vectors to create the vector space. So it's sort of like, I've made this little tongue-in-cheek comment before as well, that a set of vectors will always span whatever they span. So if you build your V, if you create your vector space as being the span of something, well, then those vectors that you use, they are by the very nature of it, a spanning set for that space. Okay, so these vectors, before I even take a breath, they are already halfway to being a basis for V. Because to be a basis, I have to span V and I have to be Li. Well, guess what? These vectors are automatically a spanning set. I don't even have to think about it. And that will always be true whenever your V is expressed as a span. So keep that in mind. We have a spanning set sort of handed to us automatically. Does that point make sense to everybody? This is important. If my vector space, this is some weirdo vector space, right? This vector space is none of these, right? This is something I've grabbed some vectors out of the blue and just formed their span and said, voila, here's what V is. And I don't really know the nature of it very well yet, but I do know that those vectors that I started with, they are a spanning set for whatever they span, or whatever their linear combinations can be. Okay, but the real question here though is that they also have to be Li. And we have not talked about that yet. These vectors have to be Li. So you know what I'm gonna do? I'm gonna do my Li test. I'm gonna do the Li test. So I'm gonna lay these vectors, but as it says up here, I'm gonna lay these vectors into the columns of a matrix. So the first vector, the first matrix goes into the first column. It's 1, 3, -1, 2. The second vector is 0, 0, 0, and 0. That goes in the second column. The third vector is -1, 4, 1, and 1. The fourth vector is 5 and -6 and -5 and 1. And I'm going to augment this with zeros when I'm doing the Li test. Okay, so it would be something like that. And what we need to do now, guys, is just hit this thing with the EROs. Okay, and keep in mind, I'm doing one of your homework problems for you right now. So you're all going to get this one right, I hope. So here's the first ERO. I'm just going to put my pivot right there on that first upper left corner. If I take -3 times the first row and I add that to the second row, I'm going to get 0, 0, 7, -21, and 0. And if I add the second row to the third row, I actually will completely get that third row zeroed out. And if I take -2 times the first row and I add it to the third row, I'll get 0, 0, 3, and -9, and 0. So I'm going a little bit quickly through this part of it because this is just the ERO business. But that's what we would have. And let's just do one more step here, guys. I will leave the first row the same again. The second row, I'm going to divide through by 7. That gives me a pivot right there. And then actually, you might notice that the last row is actually just a multiple of the second row. So I can zero out the last row. The third row is all zeros, but the fourth row is also all zeros. So that is actually your row echelon form, okay? And when I'm thinking about the LI test, you know, I've got these constants here. These are the unknowns of this little system that I'm working on behind the scenes. And the question is, you know, do the constants have to all be zero or not? In other words, are there any free variables or not? What do you guys think? Are there any free variables here?
Yes.
Absolutely. Which ones are free?
C2, C4.
C2 and C4, right? So C2 and C4 are free. And if there are free variables, then the vectors fail the LI test. They are not LI, okay? And that's the reason that I said a few minutes ago that I know that these are not a basis. They're not a basis because they're not LI. But the question remains, find a basis. And if this is not the basis, the question is, well, what is the basis? If this doesn't work, then does anybody have any thoughts what we could do to get our basis?
We have to solve for the three variables.
We really don't need to do any more hard work. The work that's up here in blue is already the hardest thing we have to do. Quentin, do you have an idea?
Get rid of the ones with the vector.
Did everybody hear that? Get rid of the vectors that are going, that are lined up with those free variables. Guys, if this column wasn't here, and if this column wasn't here, then you wouldn't have had any free variables. So just imagine that we didn't have those columns. Well, that would mean that we wouldn't have had these columns, which would mean we wouldn't have had these columns, which would mean that we would not have had these vectors. Let's take $2,000 back for a refund. Let's get rid of those two vectors because these two vectors alone, if we had started with just these two, we would have set up our matrix with this column, and the zeros. And we would have done, the EROs would have worked the exact same way, but we wouldn't have had any unpivoted columns. So we would be able now to say, hey, we have our basis. So the basis for V that I'm looking for here would be, first of all, 1, 3, -1, 2, and then secondly, -1, 4, 1, and 1. Like so. That's your basis. And you can, now you can tell me what the dimension of V is. What is it? 2. You just, how many vectors do you have in your basis? That's the definition of the dimension. So it's a two-dimensional vector space. So now we really know that V is not M2 of R. Sure, the vectors look like 2 by 2 matrices, but we're not talking about all 2 by 2 matrices. Only the ones that we can make out of these two vectors. Are you with me? By the way, guys, the zero vector, nobody should ever be spending $1,000 on the zero vector. It is never going to be LI. You will always want to get rid of it. But this one might not have been as obvious. It might not have been as obvious that this last vector, actually, we can also make that vector from the other two. And so let's not spend $1,000 buying that vector. Let's get rid of it and just keep the two vectors here that formed our linearly independent set. They're still going to span V, right? These two vectors span the exact same thing as all 4 of these vectors. We need to get rid of this intuition that the more vectors we have, the bigger the space that they're going to span. Guys, I can make you a very, very small vector space that has lots of vectors to span it with, right? I could come in here and I can spend thousands of dollars making a whole bunch of vectors, $5,000, $6,000, whatever you want, right? You look at this, you're like, wow, I form all linear combinations of those 7 vectors. This must be a huge vector space. Not at all. You would be getting rid of all of these. Can you tell I like this stuff? I really do. You would be getting rid of all of these except for the first one. I won't trip. I see that I need to fix my shoelace. This is all I need. Just this one vector would span the entire vector space. It's only one dimensional. It's only one dimensional. Make some sense? You feel pretty good about this, or you want to see one more of these? See one more? Should we do one more? The next one, I might just skip the EROs, if I could, just because that's the boring part now. Of course, I would never call it boring, and back when we were learning it, I'm sure I was super stoked about it, but now the EROs are kind of in the background. Yeah, okay, we'll do one more real quick one, and then I'm gonna have you guys do a little group work. So here is another warm up, we'll call it number 4 in my list. Find a basis for V, which is going to be equal to the span of, this time I'm going to give you some polynomials, 1 minus 2x plus 3x cubed, comma, 2 minus 5x minus 3x squared plus 6x cubed, comma, the next one is x plus 3x squared, comma, 2 minus x plus 4x squared minus 7x cubed, comma, 5 minus 8x plus x squared plus 2x cubed. Okay, I'm making this kind of long and messy on purpose to just show you, kind of how we can boil this down pretty nicely. By the way, so on this one, I'm going to say the exact same thing that I said over here. These 5 polynomials, they are already a spanning set for V. There's not even a question about that. I don't have to test them or anything. They are a spanning set for sure, because V was created, I'll just say it again, V was created as the span of those vectors. So of course, these vectors are a spanning set for that. They are a spanning set for whatever they span, okay? Kind of just automatically true. The question comes down to linear independence, right? That's really what it's going to boil down to. Can anybody tell me, without even hardly taking a breath, whether these vectors are going to be Li or not? In other words, let's not do the Li test. That's going to be annoying to write out a big, huge matrix. I don't want to do the Li test right away. I just would like to know if they're Li. How many polynomials do I have there? I have 5 of them, right? What universe do these polynomials seem to be living in? P3 of R. What is the dimension of P3 of R?
4.
It's only 4, right? So you can already kind of surmise that I have too many vectors here. This is 5 vectors in a 4-dimensional universe. So that's, K is greater than the dimension of V. It's an automatic no, right? So I know that these are not a basis. So in fact, let's write that down. It's obviously clear that they're not Li. Both of these two things, I was able to figure out without having to break a sweat, right? I can just kind of look at what I have and I know that that's the case. Now, to actually find my basis, that means that I need to throw away some of these vectors, just like I did on the last example. Let me just be very clear about this though, guys. You cannot just start throwing away vectors randomly. You have to throw away the right ones. Notice here, I threw away the 2nd and 4th vectors. That was important. If I'd thrown away a different vector, I might have been, messing it up. I can give you a really good example of that. What if you looked at these vectors and you said, oh yeah, these are LD, so I better throw something away and get my $1,000 back, and you throw this one away. And you keep these vectors. Well, now what you've just done is you kept the two vectors that were causing the problem, right? The 1, 1, 1 and the 2, 2, 2 are scalar multiples of each other. Those are still LD, right? So let's not get too sloppy, just say, oh, I'll just throw away vectors at random. We can't do that. We actually have to, at this point, we actually do have to make the matrix, just like I did before. So I guess I'll do it. I'm gonna put these vectors into the columns of a matrix. The first polynomial has a 1 and then a -2 on the x term. There's no x squared term, and there's a 3x cubed term. And then my second polynomial is 2 and -5 and -3 and 6. My third one has no constant term. There's 1x, 3x squareds, and no x cubed term. The fourth one is going to be a 2, a -1, a 4, and a -7. Doesn't it feel weird to be filling out the matrix column by column? Back in chapter 2, it was always row by row. But this is how the nature of the material changes here. We actually have to do columns now. So we lay out those 5 vectors into those 5 columns, and we augment it with all zeros for the LI test. We already know it's going to fail the LI test. It's not LI, but this is the way the matrix would need to be set up. This time, I'm not going to do all the EROs, guys, because I just don't want to spend the time on it. If you're interested in just practicing for yourself, you can check this, but I'm just going to go straight to the row echelon form. The first row stays the same. That's not surprising. We leave that one alone. The second row does change a little bit. It's going to become 0 and then 1 and then -1, -3, -2, augmented with 0. And then the third one has a 0, a 0, a 0, and then a 1 with a 1 and a 0. And in this case, the last row is all zeros. That's the row echelon form that you would end up with. Don't get too caught up with getting rows of zeros, though. I've made this comment before. What's important about this problem, guys, are the columns and the pivots. We can see that there are unpivoted columns. That's giving us the free variables that are leading us to having a no on the LI question. Free variables means no. And here I have free variables, namely the third one and the fifth one. Those don't have pivots. So I'm going to do exactly what I did last time, which is I'm going to get rid of the third and fifth vectors. So I go back and I kind of cross off those columns that corresponded with those vectors, which means I need to get rid of this vector here, the fifth one, and the third one. The other vectors, the other 3 vectors, let me just kind of circle them here like that. 1, 2, 3. Those 3 vectors are my basis for V. The other 2 vectors are simply redundant. They are in linear dependencies with those 3, you see. So we keep those 3 as our basis and we're good to go. Does this kind of make sense? It's a 3-dimensional, this one has a dimension of 3. Yes, Eric.
So our final answer, stating that is the basis of V, would it just be the curly brackets and then those 3 polynomials?
Yes, yeah, it would be. Yeah, so I just was being lazy.
Yeah, okay, yeah.
And not rewriting them all out again, but it's this guy, and this guy in a set.
Okay.
Yeah, exactly. That's right. So this is a 3-dimensional vector space inside of the universe of P3 of R, which itself was 4-dimensional. Yeah. Clear enough? Okay. What I'd like to do next, if we're all good on that, is does everybody have this group work? I tried to go around right before class and pass this around to the different tables. I'd like you to grab, I have more copies if anybody's missing this, but I'd like you to grab 2 or 3 other people and let's use all the whiteboards. We can spread ourselves around and just these questions right here on this sheet. Let's see how far through we can get on this and I'll come around and give you a hand. Luis, hopefully you can help me too. Thank you so much. All right, let's do it. Let's do it. Group work number 7.
Would there be any easy way to tell that, or like prove that these still span the original?
Because I threw away some stuff, you're nervous that I've lost the scanning.
I know they don't.
Well, the reason is that these things I removed, they are linear combinations of the other ones.
Right.
So if I just have the other ones, I would be able to remake this vector out of those two if I wanted to. So it's almost more of the conceptual point of view than anything else. But yeah, you don't lose anything by going back for a replay.
I mean, there's no way to make basis for something like that has like where the basis isn't the exact same as the.
Good. But there wouldn't be one size fits all procedure for that. Yes, let's erase this board, sorry. Get this thing erased here. Yeah, go ahead, guys. You guys can look. Okay.
All right, team.
The big buck's small. All right, no, it's okay.
Yeah.
Right, so the roads have to have a third. So that third, I'm gonna encourage you to change this thing in a way that makes it obvious that we're not. Yeah, my first suggestion here is I would recommend that it says line of spanning set. We do have a preset process. Right now. South of variables. That's what you're gonna want to do. Big things. Then I slide that matrix. Oh, in a way that sort of reflects the condition. You're on the right track, definitely on the right track. Find a spanning set for if you remember the three steps.
So like I am the person we want them, right?
Right, okay, I'm gonna remind you, the first one is right click or the vector. Number two is bust out the variable. Remember this? We didn't talk about this today so much. The last couple classes we had. The third one is to make your list, make lists of vectors. The big thing is you've got a 2x3 matrix. You need to fill it out. This variable. So that the rows add. I know we did want to use that 2x2 matrix. Class. Stay there, be there, be there. And then this thing we have to. Wow. The form of the 2x2 matrix. I want you to do the same kind of thing. But the condition this time is not. It's all just roll by roll. Oh, so.
Like this would be.
Partner, that you have, I'll come back and help. And this is not the general form. So when I hear for some of this here, That's cool. And I wanna just test. I'm not really asked that. Yeah. It's just, to give that another try. You are. Now I see.
Oh, yeah. Okay. Yeah.
Does anybody need a hand? Yes. Well, okay, did you do that?
I don't know, I just like. It's just.
That's it, except you don't need the two terms of. That's right, you don't need those two terms. The first thing, already enough. Okay, anybody need help? That looks right. Right. This is the right form. Bust it out. Oh, you guys doing okay back here? Good job, good job. Anytime you take a stand, you don't have to check anything else. It's just automatically. Automatically. Anybody need a hand? Oh, yeah, Kevin, what's up? Check the answer? That's it, that's it. You got it, and because you got this span, You know, it's not, anytime they can span, anything, was a Sunday, so that justifies one, by finding a spanning set. So that you have a subspace, that's it. Why not? Good job, good job. Okay. Hey, you guys see that?
Yes.
Oh, yeah. Yeah. That will be a little fast. Yeah, that's exactly.
Yeah.
So this. I kind of. Something like that. Yes, that's the problem. That's this. In this case, you can choose to do the ER. Anybody need a hand?
No, it's not that far.
So it- Maybe to interrupt you anyway. Yes. So if you want it. You got it right here. You got it right here. This is a 50. So it's. Anybody need help? Okay, back there? Okay, got zero. This class, guys, bad, those were bad. Determinant 0. Not alcohol, and the column that is not. So. Whatever you're thinking about. Okay. You know, that matrix. We have another we are, might be holding for less than. You can just determine. I just think it'll be easier than some of them, I don't know. I think if you just say on the determinant, and you want to. That's gonna mean the answer is no. And
Yeah.
then the determinant is not zero, and that would be the good one when it's zero. Determinant equals 0 is bad, determinant is not equal to 0. So this is. You might have. So. It's too late. Hey guys, you guys are all doing super good on this. I can see most of you are most of the way through, or at least you know what you're doing. If you'd like to take a short break right now, this would be the time to do it. If you want to get some water, go outside, check your phones, whatever you need to do, now is a good moment to do that. This is here. It says 2 by 6. So that's gonna throw out. So you know what you're doing. You know, if it's something that's right, I got to then you cross out. I mean, if you're knowing that's the right answer based on that. You know, so not even way to take it off, but you want to look at your thing. It's not. It's good, it's good. Yeah.
Then he checked the determinants when we are.
Yeah.
We didn't even know. I saw him like, oh, wait, it's just like, oh, we're doing it, dude.
Did you start to move?
Yeah, we're starting it, we did in the basement a little bit. I was just taking my time, just trying to learn it. I used to, I rush through a lot of things, everything you have to do.
Looks good, guys. Nicely done. Awesome, awesome. Hey. We're getting this. I like to see.
Yeah, practice in the basement, it was kind of helping. You know, sit down, what's wrong?
I'm a little scared. No, no face, no case. A little bit. No face, no case, you know? Didn't know I exist. I have I think an hour gap. In my training guide.
Where's your next one? Single?
No, the EC. Yeah.
What the hell?
Really? What's your longest day? Just. Oh,
So Thursdays has been later.
this class is till 4?
Good class, but it's three.
Oh, yeah, that's crazy.
Thursdays, I started late.
Oh, yeah.
60. So we're trying to turn the light.
Oh, already? Oh, that's loud, dude.
We're trying
People are listening.
Any more years?
Whatever values of those
It's like why?
then also have another.
It's like already made one round. That's why I'm
So I did a post. Yeah, so we want the source plot definition.
Good luck. God justice Lord.
Yeah.
Yeah, if not trying to have like any values, just like what you guys.
I was so ready.
Like, you're so- I don't know, I come.
I don't know if it's right.
I come, I keep the drink at home. 'Cause I'm not- Have a school.
And you're like, yeah, this is why I stand up here.
Shut up. I'm so tempted to find like someone just resell it. Wow. He's like, oh, it might be this guy. Okay, I'm like, bro, this is the first time I've finished any school. It's like, hey, school's like, this one's forever.
I love the nitro.
Sweater.
Thank you.
I got to see them in the Griffin Park, Griffin Theater. Griffin, you know, where it's pretty cool.
Right, everybody, I think
You want
we
one?
got most
Very
of
good.
you back. Think that's the case anyhow. Hopefully everybody's on their way back, but thank you so much for your efforts on these group works. Don't forget that they are in Canvas, and there's also an entire folder with all the solutions to these. So if you need to review this, which actually is probably a good idea to do that at some point, just want you to know, you can review these problems again and look at the solutions. These problems I write myself, so you know, I obviously wrote them thinking that they're good questions to practice, and I definitely encourage you to also be reviewing them when you have a chance. What I'd like to do next is try to more or less finish up this chapter 4. We're probably going to have a couple of loose ends, maybe that we'll talk about next week, but there's a couple of sections that I kind of like to just talk about together. It works best to do this together. And then just in case anybody's keeping track, we're pretty much just skipping section 4.7. We don't have time in Math 250B to go over it. It's actually a nice section, but you'll learn all about that once you switch to your major to math and you take Math 307, which is our math major linear algebra class. But we're going to move on to 4.8 and 4.9, and I'm going to talk with you guys for a little bit about 3 subspaces that we can associate with any fixed matrix. So if I give you a matrix, there are 3 subspaces that we can associate with it. I think just to have an example running along through this entire conversation, I'm going to make a matrix right now. I'll try to do my example in blue writing, so you can always kind of pick that out from the rest of this. Let's just make a matrix A, which is equal to the following matrix: 1, 2, 6. And then the second row, I'm going to make 2, 1, 6. And the third row, 0, 1, 2. And the fourth row, 1, 0, 2. Okay, so just so we have an example, this is a fixed matrix. Can somebody remind me what is the size of this matrix?
A 4x3?
Right, this is 4 by 3, right? And let's just remember that the M is the first number, that would be 4, and the N is 3. So this is telling you the number of rows and the number of columns. Okay, so nothing too weird about that. That's just an example of a matrix. And now I want to talk about 3 subspaces that we can associate with any matrix like that one. Okay, the first of those subspaces is one that you guys already know about. It's called the null space of the matrix. So number 1 in my trifecta of subspaces is the null space of A. Let's remember what this is. This is just review. These are the set of vectors, I'll call them X, that are in Rn. Such that A times X is equal to 0. Okay? And so this is a subspace, so let's just remember that, I had you watch a video a week and a half ago or so. It was a long video, and one of the examples of subspaces was anytime you look at a null space. So null spaces are always closed under addition and scalar multiplication. They do form subspaces. And, but it's a subspace of what? We always have to clarify, like, what's the big universe that we are looking at to have a subspace of? Can somebody tell me? The null space is a subspace of what vector space?
Or
It's on the board already, guys. Rn. Exactly, Rn. See, the vectors that are in the set, they are vectors in Rn. So this is a subspace of Rn, and we already know that, okay? And, you know, we also kind of know how to find a spanning set for this, and a basis and all that good stuff. So let me just remind you about that. Basically what I'm gonna do is I'm gonna take my matrix and I'm gonna do EROs on it. Well, actually, I'm sorry, let's not write the matrix quite like that. We need to augment this matrix, right? I need to augment this matrix. So let's go back to our example. 1, 2, 6, but now I'm going to augment that with 0. And then 2, 1, 6, I'm going to augment that with 0. 0, 1, 2, and then 1, 0, 2, but we're augmenting everything with 0. And let's not forget that there are unknowns. I'll call them X, Y, and Z here. Sorry, I'm using the very bottom of my board here. Those unknowns are associated with those columns, okay? And if I want to solve for the null space, I'm just going to solve this system by Gaussian elimination. So I would have to do EROs. I can see already that the first row is good to go. I have a pivot in the upper left corner, just like I want to have. And I'm actually going to move the third row into the second row so that I can get my second pivot immediately as well. 0, 1, 2, and 0. And because I want to move along, I am just going to tell you what happens with the rest of the EROs, which is you are actually just going to get everything to get zeroed out. So there won't be any more numbers in this matrix. Okay, so this is going to be your situation. Again, the first equation is really, you know, x plus 2y plus 6z equals 0. And then the second equation is y plus 2z equals 0. That is your system. That is your system of equations that goes with these two rows. And as you can see, the z variable, which is the third variable, is free. So z would be a free variable. I'm going to label it as t. So this is not the first time you guys are seeing this, right? We've even done examples of null spaces before. I'm just kind of reviewing it again with a new example. So you set up your free variable, which is z. Then you have to solve for y. Okay, well, y is equal to negative 2z. So in terms of my free variable, y would be negative 2t. Okay, and then, well, what about x? Let's see, x is, if I solve from the first equation, x would be negative 2y minus 6z. So I'm going to see if I can do this in my head. So if I solve for x, negative 2y is actually 4t, and then I subtract 6t from that, I actually get another negative 2t here. Okay, so there's your x, y, and z values. And so your null space of A is the set of the vectors negative 2t, comma, negative 2t, comma, t, such that t is a real number, right? So we would put it in this kind of a set notation. Okay, But, so that's finding the null space. But the question that's maybe a little more, new for us now would be, what about finding a basis for this null space? And you even have some questions on that from 4.6. Finding a basis for this null space. Well, as you could imagine, you need, part of being a basis is just having a spanning set. You need to bust out your variables, right? And if I bust out my variables, so basis, the basis for this null space. If I bust out the T from everywhere, if I bust that T out, would you guys agree that I just get -2, -2, and 1? Yeah, that's it. So it busts out the T from the general form. Right, write down the general form, bust out the variables, make a list of the vectors that remain, that's it. That's your basis. Okay. So in this example, what would be the dimension of that null space? Just one. The dimension of anything is just the number of vectors that are in the basis. Well, there's one vector. This is just one vector, so the dimension is one. There is a name for the dimension of a null space, and I want to get it into your notes here. I'll go back to my black marker now, because this is a general definition. Anything that's general, I'm trying to do in black, and then the example is in the blue. So the dimension of the null space of A is called, it is called the nullity of A. It is called the nullity of A, the dimension of the null space. So in our example here, we can go back up here and add that in here. The nullity of this matrix is equal to 1. There's one basis vector in that null space. Okay. So far, is everybody good with this? Actually, there's not a lot here that's new. Pretty much everything other than this word nullity, that's new. But everything else is kind of, should be pretty comfortable. You know, you set up your system of equations, you solve it by doing EROs and back substitution, you write down the solution set. We were doing all of this 2 chapters ago, right? The only thing that's new is the whole, oh, I'm gonna bust out the variable and make my basis. And then how many vectors are in that basis, we're gonna call that the nullity. That's all that's really new up here. But I actually do want to show you a little insight about something. And this is like the easiest theorem in linear algebra to understand once we sort of explain it. I would like to understand, why is this answer 1? From a very grassroots perspective. On this example, why is the answer 1? Well, it's 1 because there's one basis vector. Why was there only one basis vector? Well, that was because there was only one free variable to bust out. Right? Why was there only one free variable to bust out? Well, when I look at my row echelon form, I had only one unpivoted column. Right? You actually see that that's the key to the reason that the nullity turned out to be 1 over there, is because there was only one unpivoted column over here. The nullity of a matrix, let's just make this as a remark. The remark that I would add right now is that the nullity of a matrix is equal to the number of unpivoted columns in the row echelon form of A. It's how many non-pivots you have. Does anybody remember what we called the columns that do have the pivots, or what was the word that goes with that? If I want to associate pivots, say it again, the rank. The rank of a matrix was the number of pivots or pivoted columns. So I would just like to recall that the rank of A is the number of pivots. And let me just write that slightly differently. I'll just say pivoted columns in the row echelon form. So are you ready for the easiest theorem in linear algebra? The one that you could explain to anybody on the street in no time at all. Well, that might be going a little too far. But would you guys agree with me that every column of your matrix either will have a pivot or won't have a pivot? It either will or it won't. Some of them have pivots, some of them do not. But in total, if I add up all the pivots to all of the non-pivots, I'm gonna end up with all of the columns, right? Every column is either pivoted or unpivoted. So you know what? If you add up the rank to the nullity, you have to get all the columns of your matrix. It is the famous and easy theorem called the rank nullity theorem. I want to write it here for you guys. This is a nice one. It just says for any matrix, for any matrix A, which is M by N, if you take the rank of A and you add it to the nullity of A, you must get N. You must get N because the total number of columns is N. And that number is made out of two parts. The columns that have the pivots and the columns that don't have the pivots. If we go back to our example, we can see over here that there are two pivots. And there is one unpivoted column, that's the free variable that we ended up with. And the total number of columns in the matrix, which is N, is 3, you see. So that's what we started with here. So this is just verifying the rank nullity theorem. So if you want to explain this theorem to your friends, it's really easy to do it. You just say, look, count how many columns you have, right? Every column is either going to be pivoted or unpivoted. And altogether, that means when you add up the rank and the nullity, you end up with the total number of columns. This all making sense? Pretty simple theorem. Okay. Well, this is kind of nice because usually you're going to know what N is. You're looking at your matrix and yeah, I've got 7 columns or whatever. You're going to know what this number is. And so you can play this equation. You can play these two quantities off of each other. If you know what the rank is, you can solve for the nullity. If you know what the nullity is, you can solve for the rank. Kind of nice to be able to go back and forth like that. Yeah, okay. That's about all I got to say about the null space. Most of this is stuff we had done before. I just wanted to kind of write it down again. Are we good on that? Okay, let's go on. I said there's 3 subspaces associated with a matrix, and so far I've only talked about the first one. Let's go to the ones that are new that we have not seen before. This is going to be number 2 in my list. The second one is something called the row space of A. Okay, so this is subspace number 2, the row space of A. And this is just going to be the following set. It is going to be the span of the set of, and I'm going to put this in words here, the row vectors of A. I'm just going to think of it as the span of the rows of the matrix. Now, the first thing I'm going to write down is that this is a subspace. Can somebody tell me why? Because it's the span of something. Anytime you say take the span of anything, you always get a subspace, right? I must have said that 20 times by now. For the last couple of weeks. So this is a subspace. Subspace of what? Well, let's see if we can get this right. If I look at my rows of my matrix, right? Each row has a bunch of slots in it. Well, how many slots is it anyway? So this matrix had 3 slots in each row. Well, the 3 is coming from which number? The N, right? So this is actually a subspace of Rn. I'm trying to be clear because there's also an M floating around, but this is a subspace of Rn, which is actually the same as the null space. They are both subspaces of Rn, okay? And so if we look at our example again, let's go back to the blue marker. If we go back to our example that we've been working on, the row space of A is just the span of, let's see, the first row was 1, 2, 6, and then 2, 1, 6, and 0, 1, 2, and 1, 0, 2. This would be the row space of the matrix in part A. However, we've been doing some examples already today that were not that different from this, where I sort of looked at this. If I ask you about this, would you tell me that this is 4-dimensional? I hope not. I hope not, because after all, this is a subspace of R3. That means even my giant universe that this whole entire thing is living inside of is only 3-dimensional. So this is not 4-dimensional. Remember the example we did earlier with the 5 messy polynomials? And we've realized that they were actually LD and we had to remove some of them. Well, that's exactly the situation again right now. I have 4 vectors here and they're living in R3. It's too many. It's too many vectors for these to actually be a basis and make this the determining set for the dimension. It's not 4-dimensional. So what do we have to do? If we want to figure out what the dimension and the basis for the row space is, that would be, I guess that's a good question. How to get basis / dimension for the row space of A? That's a question that would be good to ask. The answer is not to just graph the rows. That's too many. They are LD. What we actually need to do is we need to take the non-zero row. So here's the answer. The answer is take the non-zero, i.e. pivoted, the non-zero, i.e. the pivoted rows of the row echelon form of A. And use that as your basis. So again, going back to our example, the basis for our row space of our example would be just the non-zero rows of this row echelon form. That's just these first 2 rows. So that would be 1, 2, 6 and 0, 1, 2. And so because of that, of course, then the dimension of this row space in this example that I'm doing right now, the dimension of this would be equal to only 2. It would be equal to only 2, right? Because there's only 2 vectors there. You see, these 4 vectors were LD. And in kind of a twisted way, if you want to think about it, the EROs that you did over here, they sort of exposed those linear dependencies. They massaged them out into these rows of zeros that ended up at the bottom of the matrix. The only things that survived were the first 2 rows. Guys, when you do EROs, you don't change what the span of those rows would be. The row space is the span of the rows, but you don't hurt that by doing EROs. Think about it. If you permuted 2 rows, if you did a PIJ, all you're going to do is switch the order that something's listed in here. That's not really changing the essence of the linear combinations that you can make, right? So permuting two rows, that does not affect your row space. If I multiply a row through by 10, so instead of having 1, 2, 6, now I've got 10, 20, 60. Still doesn't matter. I can still build the same linear combinations out of those vectors as I could from the original vectors. It's not affecting it at all. So you might as well, instead of taking all linear combinations of these vectors, you might as well just think of it more simply as I'm gonna take all possible linear combinations just of these vectors. So much easier. And these vectors are actually a basis. They are Li as opposed to the original set, which are LD. You see? That's my point. Okay, great. And by the way, so in general, back to the black marker again, in general, the dimension of the row space of A I think I want somebody other than myself to answer that. What is the general, so we've got the dimension of the null space is called the nullity of A. What is the dimension of the row space going to be? We have one example in blue if we need help. But what do you think the formula would be in the general scenario? Let's see, the dimension, let's just, I realize that we've learned a lot of abstract stuff lately.
The rank of A.
It is. It's the rank of the matrix. Why is that? Well, what is the base? How do we get the basis for the row space? Take the pivoted rows of the matrix. Well, that means you're taking as many rows as you are pivots. Okay, if there's 2 pivots, your dimension will be 2. It just matches with the rank. So this is the rank of A. Absolutely. That is the rank of A. So this is a good one to know, for sure. It's kind of interesting, isn't it? The null space and the row space are subspaces of Rn. Right? They're both subspaces of Rn, but their actual dimensions within Rn are not the same. The dimension of the null space is the nullity of the matrix. The dimension of the row space is the rank of the matrix. On this example in blue, we have a 2-dimensional row space and a 1-dimensional column space. A 1-dimensional, I just gave away the third one. A 2-dimensional row space and a 1-dimensional null space, right? Inside of this R3. Basically what we have. Kind of cool. Clear enough so far? I just got one more for you. We're just about done. One more thing here. Ooh, I just erased my matrix. Not really want to do that. It's okay. Let's do number 3. So slip of the tongue, I already let this one cat out of the bag. The third subspace is the column space of the matrix, which we write as col space of A. And nobody's going to be shocked about this one. This is literally just going to be the span of the column vectors of the matrix. So the span of the set of the column vectors of A. And let's just think about these columns, because of course this is a subspace. It's a subspace because it's a span, same reason as before. And subspace of which vector space? We look at our columns and ask ourselves, well, how many slots do those vectors have in them? Because that dictates kind of what the universe is that you're talking about. So in this example, it would have been 4, right? And sadly, I erased some helpful information over here. The matrix that we were given had 4 rows and 3 columns. It's the 4, which is the M value that we want to keep track of here. Okay, so let's be clear. This one is a subspace of Rm, not the Rn that we saw on the other one. Okay, so this is a subspace of Rm. And so it's just the span of the columns. Okay, but the question that everybody's gonna want to be able to answer is how to get basis / dimension for the call space of A. Asking the question again. So the answer for the row space was to just take the pivoted rows of the row echelon form. And that was perfectly fine because when you did row operations, as we just discussed, you don't harm the span of those rows. Unfortunately, that's not true for the columns. If you do EROs on a matrix, you're gonna mess with the columns. You're gonna mess them up a little bit. So we have an answer here that's a little more, it's not any harder to work it out, but it's a little bit more to write it down. It's also a lot more to explain it. Certainly not gonna do it right now. So I'm just gonna tell you this one, okay? This is my freebie answer for the day. We're just gonna kind of learn this one. Basically, what we do is we take the pivoted columns. So instead of the pivoted rows, from A, we take the pivoted columns, not from the row echelon form of A, but from A itself. That correspond, let's just say that appear in the row echelon form of A. And I'm not 100% sure that I wrote that out as clearly as I possibly could. Let me just, with the example, it will be very clear. So all I'm saying, not to make this sound that crazy, you just take your row echelon form of your matrix. Admittedly, you did row operations here. So I'm not just going to take the pivoted columns here because the columns have been messed up. But what this is trying to say, if I said it right, this is trying to say you take those pivoted columns and you just find the corresponding ones over here and write those down. As long as you're writing down columns of your original matrix, you are definitely in safe territory, right? You're certainly okay. It's when you go to the row echelon form of A that the columns have sort of been, they've been banged around a little bit. While you were doing those EROs, you're gonna change the span of those columns and you don't want to be working with the wrong matrix. So you take these pivoted columns and you go back to the original matrix. So in the example, the basis for the call space of A is just, it will be written as a set. By the way, you might have noticed when I was doing the row space, I wrote the rows as rows. I wrote them horizontally. Now, if I'm talking about columns, you're gonna notice I'm gonna try to write them so they look like columns, right? So they're gonna be kind of up and down a little bit. So the first two columns here are pivoted. So I go back to here and I grab the first two columns, 1, 2, 0, 1. And the second one is 2, 1, 1, 0. Okay, and because you are choosing your basis vectors according to your pivots, because you're doing that, your dimension of your column space is still the same as the number of pivots, which is the rank of the matrix. So the column space and the row space are both subspaces of the column space and the row space, they both have the same dimension, the rank and the rank, but they live in different universes. The row space is a subspace of Rn. The column space is a subspace of Rm. And I am out of time, but I kind of wanted to show this to you, but my stupid screen is not coming up. Can you see the sideboard over there? If you scroll down to the special handouts folder, I have a little document in here. I know it's hard to read because it's so small. It's called Recap Summary of 4.6, 4.8, and 4.9. I just wanted to point out down here at the bottom, this is something I would print out and put under your pillow at night for the next 2 weeks. It will be really helpful. This thing here is simply a chart that has, I know you can't read it very well, but it says null space, row space, and column space. It describes what each of them is, what their subspaces of, what their dimensions are, and how to get a basis for them. So if you fell asleep for the last 30 minutes and missed this lecture, the entire thing is right there on that half sheet of a handout in Canvas. So, guys, thank you so much. I'll be downstairs after 5:30 if you've got questions for me. I am gonna make a video for some of those homework problems. So I'll send that out to you probably tonight. Have a great rest of your Thursday, everyone.
Everything homework.